Well, welcome back, everyone. Well, I had quite the adventure with these little inexpensive Chinese lithium-ion charger circuits. Did a few postings on Facebook, and one of the viewers mentioned that it was one of the, weren't careful, it was one of the best lithium-ion grenade makers he's known. And I guess his point was that charging current, of course, is important anytime you're charging batteries. Not only how you charge them, how you know, the cycle itself, but also you have to watch that you're not charging a battery too fast, it'll overheat and so on. And so the circuits that I had showed you last time in that video, which was this one, which was hardwired, which is, I got to show you something about that, but then also the USB version here. Now the USB version is actually set up to have a maximum charge current of 1 amp or 1000 milliamps, and that's fairly hefty, so you'd have a pretty good sized battery when you're charging that. Now I'm pretty sure these ultrafires, it would probably be alright to charge those. These are 3 ampere hour batteries, so 1 amp, that's, you know, like 33% rate. That's not so bad. I don't think that would, they would heat up from that. But if you're charging a smaller one like this, these are only, get this flipped around here, 900 milliampere hour. So this one you would want to charge at a lesser rate, and that would be a bit much. Now that being said, I've charged both, but there's a caveat with that, in that because this is a USB one and I had it plugged into the PC, typically, if I remember right, the PC's USB port's limited to 500 milliamps, so that might have kept it from charging the smaller batteries too fast. But still, it's a concern, because there are USB ports, they will put out more than, or deliver, I should say, more than a half an amp. And then the other thing I found out with the other circuit, the one you would solder wires to instead of having the USB port on, these two here, is evidently, from what I'm seeing, the resistor that you use to, quote, program the charge current with is not on these boards. You have to put that resistor on. So it's something to keep in mind if you buy the kind you have to hardwire in. You know, you have to figure out what current you want maximum during the charge cycle, and then install that resistor to set that up. Okay, now here's something else I found out. This, and it really threw me for a while. This is a data sheet, I'm poking myself with my tweezers here, data sheet for an LTC 4056, and it is a lithium ion charger. Okay, and I was trying to match, and the number on the chip, by the way, on the board is 4056. However, it's a TP 4056, and I guess I unfortunately assumed, you know. So I'm trying to match up the pin numbers and make sure that they're going to the right points on the board, and that the program lead for the maximum charging current is tying to a resistor on the board. And I was trying to see what that resistor was so I could calculate, because there's formulas for that. So I was trying to calculate the maximum current during the charge cycle with that coming from the factory that way, and which unfortunately it's set, like I said, to 1 amp, which is a 1.2K resistor, by the way. And when I was doing that, I realized these pins were making sense. For example, pin 5, which is the lead for the program resistor for the current, was on that circuit board going to the plus on the battery, and I'm like, oh, that's, what the heck's going on? And I'm looking at other leads, and pin 4 is supposed to be ground, and it's going to VCC, and like, this is, you know what, did they put a bunch of chips that were mismarked on these boards? Maybe that's why they're so cheap or inexpensive, whatever. And so I started doing a little research, because it just didn't seem quite that viable. That's what was going on. So I got a little more careful about looking up the data sheet, and looked up a TP 4056 and it's from the Nanjing Top Power Corporation, which is interesting because they are actually the people that made the circuit board too. So looking at that package, these pins down this one, these now match up correctly, and there's quite a bit of difference in this pinout. It's completely different actually. For example, like I said, pin 4 on this is VCC, pin 4 on the other is ground, and the program pin for the current on this is pin 2, the other one is pin 5, so big difference. And then there's actually differences in operation. It's still really basically the same circuit in a lot of ways. Yeah, I thought I'd give you some specs while we're doing this. Try to get into it a little more in depth. Oh, actually, input supply voltage is, goes up to 8 volts. On the other one, it's 10 volts actually. So that's a little different. What else? The maximum charge current on this one is 1200 milliamps. On the other one, I think it was 1000 milliamps. So I mean, there's some subtle differences there. Again, though, the basic operation is still the same. Now this one says, so I'm just going to read these features really quick. Programmable charge current up to 1000 milliamps. That's typical. The 1200 milliamps is maximum. It says no MOSFET, sense resistor, or blocking diode required, and I assume that's because if you reverse the polarity on the input, I could test that theory and find out, couldn't I? Let's see. Constant current, constant voltage, depending on which part of the charge cycle it's in at any particular point in time. It will determine whether it's constant current or constant voltage. We'll go over that in a minute. This may discharge a single cell, although I would like to try to set one of these up to charge 2. I have an idea about that. Maybe if I can get it to work, we'll throw that on another video. See if we can charge 2 in series. What else? Automatic recharge. I guess if it charges and then things just sitting there, it starts to die, it'll charge it again. I mean, that just seems like a no-brainer to me. But there's a 2.9 volt trickle charge threshold, which I believe means that the battery has to be at least 2.9 volts when it starts the charge cycle. If it's not, it'll trickle charge until it gets up to 2.9, then it'll go into the full charge, regular charge cycle. I think that's just to not damage the battery or hit it with any unusually large currents when the battery voltage is below 2.9. Evidently it'll cause damage. That's about it for that, really. And I don't think there's really anything else in there. Pins on. One thing about this that the other one has it. Actually, I don't see it on the other package, so that's a good thing for this one. It does have a lead, pin 1 for temp, and you can actually have a thermocouple. It's tied to a voltage divider, and then fed into this pin. And so if the battery is too cold or too hot, it'll shut the charge cycle off, which is a nice feature. No, it's not. It's not built onto these boards, unfortunately, but if you bought the chip itself and you want to etch up your own boards, you could set it up so that the temperature would shut this off. And then you get your program pin for setting the resistor current, or excuse me, the charge current, ground, VCC. Chip enable, I think, is just a way to shut the chip off if you want too quickly for some reason. I think it's normally tied to, it's actually in here, tied to, can't pick up the page when you want to. What's up with that, right? Chip enable input, high input will put device in normal operating mode. Pulling the chip pin to low will put it in disable mode. So I believe it's normally tied to VCC, if I'm not mistaken. I mean, unless you have a reason to have an alternate method of shutting the chip down, if that's something that's important to you, depending on your application, obviously. Okay. So enough of that. And you have your battery. Well, I didn't show you the pins, but you have the charge pin and standby pin. Those are tied. I should show you that. These two pins here, 7 and 6 standby and charge. Those are tied typically to LEDs, which I believe have pull-up resistors. So you know one LEDs. I can't talk. One LED is on when it's charging, and one LED is on when it's done charging in standby mode. And then another pin goes to the battery. Okay. Oh, I want to show you the graph too. In the graph here, hopefully you can see this all right. Not apologies, but this line here is the constant, well, what they call constant, well, it's constant voltage up here. So, but when the charge cycle starts, okay, the current ramps up pretty fast. And of course, as it does that, and as time goes by, the voltage is going to slowly increase. It's going to reach a point where the voltage is going to hit float voltage, and when it hits float voltage right around here, which I think I determined was like 4.1 volts, then the current's going to start dropping off, and it's going to stay at constant voltage until the charge is terminated. And I did check it. I've had a meter in series with the battery. I did one earlier. And it does literally go to, well, it wasn't a measurable charge current, at least when I had my meter on 10 amps I had to have, and you couldn't measure it, so, but it was pretty much shut off in standby mode. It doesn't charge very much at all there, I guess. So anyway, that is that. So through these 2 pages, and this is the circuit here, and this is very typical of the boards that I got from them. So this resistor is, I assume, some kind of a current limit. I'm not sure why that's there. It's not on the other, in the other circuit diagrams for that Linear Technologies chip, but it is for this one, which is what's on the board, so that's what's important. Anyway, that resistor's there. There's a cap to ground. Here's the 2 LEDs I was telling you about, the pull-ups, and actually they do go to VCC. And they have a 1K resistor in series with them to limit the current through the LEDs. And that obviously is going to vary depending on the LED you got and how much current it takes to light them up to whatever brilliance you want to light them up to. The program pin, again, that's where you set the value of the resistor for the charging current. There's a table on this page, and I'll put a link in the video where you can get this PDF, and it gives you the different charge currents and the associated resistors to establish those charge currents. And the one that's in there is 1.2K, which is 1,000 milliamps. That's how I knew it was a 1 amp charge by default from the factory. Personally, I would stick with something around 4K or 5, well, 3 or 4K, maybe 3.3K, something like that, a little less than 400 milliamps. Because those little batteries I have, you don't want to charge those too fast. And the bigger ones would be fine for the higher current. And again, the circuit boards, your technicians out there, you can change parts easy enough and change that charge current. What else do we have here? So we also over here, there's a capacitor across the battery. This is the battery with the thermocouple, and the thermocouple is tied to ground here, and then it comes down through here and it hits this point, and this is a voltage divider between VCC and ground. And because the other end of the thermocouple goes to ground as well, the thermocouple resistance is basically in parallel with this other resistor R2 to ground. So as that thermocouple changes, as temperature changes on the battery, that parallel resistance is going to change, and that's going to change the voltage at this point being fed to the temp pin on the chip, and if it exceeds or drops below whatever voltage that is, indicating too cold or too hot a battery, and it'll shut the charge cycle down. And so that's that. The formulas. Let me do that really quick. It's getting to be a long video. I don't want to run out of time here. Just really quick. They have IBAT, which is the current you're charging the battery with, equals VP PROG, which is the voltage on the program pin, which they said you could monitor, by the way, if you wanted to. I did that actually. I checked it a couple times along with the current, and redid the formula to figure out the resistor, and it came out the same. Did it like 3 times, so it seems to work pretty well. Anyway, and then R program times 1200, and I believe I came up with R, the program resistor, was equal to pretty sure it was V, I may be wrong, and I think I have the piece of paper over there yet, I'll go look, times 1200 divided by I bet. So if you know you're charging current, you could do that. There's a, where's that formula? They had a formula on the other one, and I almost want to guess that it's a similar concept, but I don't have that page printed. So, but anyway, point being is that you can take that formula. Now, I guess for the intents of determining that resistor, you can base that on V program being equal to 1 volt. And I believe actually that's true with the other one too, the other Linear Technologies chip as well. I wish I had that other formula with me here. Let me see. Threw the paper in the trash. Thought, you're not going to need that. Surprise! Okay, it's not on that one. I don't think... Oh, here it is. No. Alright, well anyways. There is formulas for doing that. And it was, let me make sure I got the formula right anyway. Yeah, so it was our program equals Z program times 1200. We could run through one, let's see. So R equals, it's 1 volt times 1200 divided by the current. If we want the current to be 1000 milliamps. I can't remember if that was in milliamps or amps. Well, let's just see. So 1 times 1200 obviously is 1200, and divide that by 1000 gives you 1.2. So I guess that would be 1.2K, and I do know if you look at the table that that is the case right here. So 1.2K is 1000 milliamps, so that is a way to come up with the resistor value for whatever charge current you want. Just change the current here, plug in whatever number you want, and of course as this number goes down, this number is going to go up. I mean, it's because it's on the bottom of the fraction. So there you are. Hope you enjoyed that video. Gives you a little more versatility with those charger circuits, and remember that it's a TP4056 and not the LTC 4056. So when you go to look up a data sheet for those, big difference. Thanks everyone for watching. Have a nice rest of the week, and we'll see you again.